Problem statement. The steady state temperature distribution in a one-dimensional wall of thermal conductivity K and thickness L is of the form T equals ax squared plus bx plus c. Derive expressions for the heat fluxes at the two wall faces x equals 0 and x equals L, and the energy generation rate in the wall per unit wall area. So here's a quick schematic of what is the problem is actually asking us. So here's the thickness of this one-dimensional wall. So here's the direction x. We know the distribution uh, uh, is given here to us. So t as a function of x is given. We want to find the values for q double prime x at 0, q double prime x at L, and we also would like to find the value of heat generation rate uh, within this wall thickness. So these three parameters are of interest for us. So in order to solve this problem, in order to find the value of uh, heat generation, we will need to write the general heat diffusion equation. So we can simply write the heat diffusion equation for a very general case first, and then simplify that. So in the very general case, heat diffusion equation would look like the following. We'll have T dx K dt dx plus partial with respect to y K dt with respect to y plus partial with respect to z of k dt with respect to z plus q dot for heat generation equal to rho cp dt over dt for the heat storage part. Now, what are the assumptions that are applicable here? Let's write those down. So the assumptions are the followings. First, I'm going to assume that this is a steady state situation. For a steady state situation, the right hand side of this equation is going to be equal to 0. Second uh, assumption is a one-dimensional conduction through the wall. In that case, this term and this term will also be 0 because we will not have any heat conduction in y and z directions. And finally, 3, I'm going to assume that uh, um, the properties are constant, so constant properties. So if that's the case, I can reorganize the equation, and it's going to be in the following form. I'll have second derivative of temperature with respect to x plus q dot over k equals to 0. Well, since I already have a function for temperature as a function of x, I can simply use that function and plug it in the equation that I just came up with to find a value for q dot. I'm going to do that. So first I will write q dot is equal to minus k dx of dt over dx, which is simply the second derivative of temperature with respect to x. Now I can plug in the function d dx. So the first derivative of that function is going to be 2ax plus b, and again I need to take another derivative of the function, so q dot will give me minus k times 2a. This is how the heat generation is found. So we have a constant value for that. Um, Now, the question also wants us to find the heat fluxes at x equals 0 and x equals L. In order to find those values, we simply can use the Fourier's law. So the Fourier's law for a 1D case is simple to write. It's going to be Q uh, double prime x equals to minus K dt over dx. Again, I have the function, so minus K times 2ax plus b. Uh, and now using the expression for the temperature gradient derived above, um, I can just plug in the values for x. So in simple words, I can use x equals to 0 and find that the heat flux at x of 0 is simply minus kb, or if x equals L, then I'll have q double prime x at L to be minus k to a L plus b.